Welcome to today's presentation. I am excited to introduce you to Chapter 2, Encoding Schemes and Number System, explore various number system conversions used in computer science. This is for class 11 computer science. So let's get started and dive into the fascinating world of number systems. What are the learning objectives? What we are going to learn? First, identify number system. Understand the base, digits, and positional value of binary base 2, octal base 8, decimal base 10, and hexadecimal base 16 system. The base is basically by how many numbers are there in that particular number system. Suppose binary system consists of 0 and 1, so its base is 2. Octal number system consists of 0 to 7 any numbers, that its base is number of digits, that number of numbers are base 8. Decimal number system consists of 10 digits, that is 0 to 9, so its base is 10. And hexadecimal number system, its base is 16, 0 to 9, and capital A to capital F is all about this number system. To convert numbers accurately between any two number systems, we rely on standard algorithms such as repeated division, positional expansion, and grouping. These tools ensure that our conversions are precise and reliable. Also, understanding why shortcut methods like converting between binary, octal, and hexadecimal work so seamlessly is key. This is because all these systems are related through powers of 2. Now let's look how we convert binary, octal, or hexadecimal fractions back to decimal. We do this by using place values with negative powers, the base, which helps us understand the fractions part precisely. We use repeated multiplication by 8 or 16 to convert decimal fractions into their octal and hexadecimal representations. For converting decimal number fractions to binary equivalent, we apply the repeated multiplication by 2 method and read bits from top to bottom to obtain the binary fractional equivalent. It's good practice to cross-check our conversions using reverse operations. This helps verify that our results are correct. Let us move to next slide. The 4 positional number systems. A positional number system assigns value to a digit based on its position. Computers use binary internally. Octal and hexadecimal are compact representations of binary data used by programmers. Here, a binary number base is 2. Digits are allowed 0 and 1. The binary numbers are used internally by all digital computers. Each digit is called a bit. For example, 1011. Octal number, the base is 8. Digits allowed 0 to 7. It can be represented a group of 3 binary bits. It is common in older Unix systems and file permissions. For example, 13. Decimal number system base 10 consists of digits 0 to 9. The number system humans use in everyday life, base for all other conversions. Example, 11. Hexadecimal number system has a base 16. Allowable digits 0 to 9, capital A to F, that means 10 to 15. Groups of 4 binary bits widely used memory addresses and color codes. For example, B represents 11. You see all four representations above: 1011 in binary, 13 in octal, 11 in decimal, and B in hexadecimal represent the same value, 11. Let's move to the next slide. Now, let us see some conversion from one number to another. Here, we are looking for decimal to other bases. The repeated division method is the standard technique for converting a decimal base 10 number to any other base like binary, octal, hexadecimal. Divide successively by the target base and collect remainders in reverse order. This is the rule. For example, decimal to binary. So for example, decimal number is 25, base is 10. How to convert? Repeatedly divide by 2 and note down the remainder. For example, 25 divided by 2, remainder is 1, again remainder is 0, the remainder is 0, the remainder is 1, the remainder is 0, the remainder is 1, and read it in reverse order. That means for 1, then 0, then 0, then 1, and the final value is 11001. That means decimal value 25 equivalent to 11001 in binary. Similarly, for decimal to octal, the pattern is same. Instead of repeated division by 2, we are repeatedly divide by 8 and note down the remainder. Remainder must be within the range 0 to 7. For example, 12510, that is a decimal number. First we divide by 8, note down the remainder 5, then remainder 7, then remainder 1. Reversely we read 175. So the result is 175 of 8. This is the octal equivalent of decimal number 125. Next, decimal to hexadecimal. Instead of 2 and 8, we are use the target base 16. Repeatedly divide by 16. Remainder 10 to 15 are written as A to F. Otherwise 0 to 9. Read remainders from bottom to top. For example, 255 is a number in decimal. We need to convert into hexadecimal. First we divide by 16. Note down the remainder. 15 means F. Then again 16. Remainder is 15F. So reverse order we read F and F. The result is FF in hexadecimal number system. Let's move to next. Now let's see converting from binary to other bases. Binary is the native language of computers. Converting binary to decimal uses positional expansion. Converting binary to octal or hexadecimal uses fast grouping shortcut, because 8 equal to 2 to the power 3 and 16 equal to 2 to the power 4. That means in octal number can be represented in a bit of 3 bits, and hexadecimal number can be represented using the 4 bits representation. Let us see binary to decimal positional expansion. Multiply each bit by its positional value, power of 2, from right to left, then sum all digits. For example, a binary number is 1101 base 2. So we are multiplying this number 1 in 2 to the power 0, then next 0, 2 to the power 1, 1 2 to the power 2 square, and then 2 cube. And after summation, well, we are getting 13 base 10, that is the decimal equivalent. This is called positional expansion. So first position's value is power 0, second position is 1, and so on and so forth. Now convert the binary number to octal. We need to represent group by 3. Starting from the right, group binary digits into set of 3 bits. Convert each group independently to its octal digit 0 to 7. For example, binary number is 1101012. We need to convert into its decimal equivalent. Now see, 101 value is 5 and 110 value is 6. If we convert 1 into 2 to the power 0 plus 0 into 2 to the power 1 and 1 into 2 square, we will getting 5. Similarly, 0 into 2 to the power 0, 1 into 2 to the power 1, and 1 into 2 square, we're getting 6. So the result is 65 base 8. Similarly, like octal, we if we convert binary to hexadecimal, we use, instead of group 3, group by 4. Okay. So starting from the right, group binary digits into sets of 4 bits, and each group its hex digit 0 to 9, A to F. For example, 10101111 conversion, we are getting A and F, that is AF16 hexadecimal equivalent. Let's start by looking at why grouping is so efficient for the conversions of octal and hexadecimal, from binary to octal and hexadecimal, and in the reverse. Since 8 equal to 2 to the power cube, 2 cube, and 16 equal to 2 to the power 4, every octal digits maps exactly to 3 bits, and every hex digits maps exactly to 4 bits. This makes binary to octal and octal to binary, binary to hex, hex to binary, octal to hexadecimal, and hex to octal the fastest conversions in computer science. They fit together perfectly because of these powers of 2. Now let's explore how grouping works in practice. For example, when converting binary to hexadecimal, we start from right and group the binary digits into set of 4 bits. Each group then directly converts to hexadecimal digit, which can be numbers from 0 to 9 or later from A to F. Similarly, when converting binary to octal, we start from right but group the binary digits into sets of 3 bits. Each of these groups converts independently into an octal digit ranging from 0 to 7. This grouping simplifies the process significantly. Let's move to next. Now converting octal and hexadecimal. Octal and hexadecimal numbers are converted to decimal using positional expansion with the respective bases 8 and 16. They convert to binary via fast grouping method in reverse. First, let's take octal to hexadecimal. Multiply each octal digit by the corresponding power of 8 and then sum the digits. Example 175 base 8, that is 1 into 8 square, 7 into 8 to the power 1 into 5 into 8 to the 0, increasing order 8 to the 0, 1 and 2. Then after summation, we're getting 12510. Similarly, octal to binary, converting to 3-bit binary equivalent, each octal digit 658, 6 to 110 and 5 to 101. The result is 110102 base 2. Hexadecimal to decimal, multiply each hex digit by the corresponding power of 16 and then sum. Example AF16, 10 into 16 to the power 1, 15 into 16 to the power 0. The result is 17510. This is a very, very similar process. And again, like octal to binary, we are grouping 4 bits. Hexadecimal to binary, group of 4 bits. And suppose AF16, converting A to 4 bits, 1010, F2, 4 bits, 1111. Then we are writing the final value, 1010, 1111 base 2. Let us move to next. Now let us see some conversion methods related to fractions. Decimal fractions to binary, multiply by 2 repeatedly. Multiply the fractional part by 2 repeatedly. Record the integer part 0 or 1 after each multiplication as the next binary digit. Read the digits from top to bottom. In the case of non-fractional, bottom to top. In case of fractions, top to bottom. We are going to record what? 0 or 1 in case of decimal to binary. For example, 0.625 of decimal, the result is 0.1012. Like how? 0.625 into 2, 1.25. We're noting down 1. Then the remaining part 0.25, 0.25 into 2, 0.5, noting down the 0. Then 0.5 into 2, 1.0, noting down the 1. Since the fractional part is 0, if we multiply with again with 2, we are getting 0. So we will stop here. So the final result is 0.101 base 2. Decimal fraction to octal hexadecimal. Here we are using multiply by 2 method. Here we are using multiply by 8 or multiply by 16 method. Replace the multiplier with 8 for octal and 16. Record the integer part after each step. For hex, map values 10 to 15 to A to F. For example, this is the decimal fraction. Result is 0.B16 hexadecimal. How? 0.6875 into 16, 11.0. That means when the fractional part is 0, we'll stop here and note down the 11 means capital B. Present both methods side by side for comparison. Okay. Reverse from binary octal hex fraction to decimal, we will use place value method. Multiply each fractional digit by its place value, negative power of the base, and sum the results. Example, 0.1012, 1 to the power minus 1, 0 and 2 to the minus 2, increasing order, plus 1 to the minus 3, that means 0.5 plus 0 plus 0.125, we're getting 0.62510. This is the reverse operation as compared to the earlier operations. For conversion of octal to decimal, instead of 2, we'll use the base of octal, that is 8. In case of hexadecimal, instead of 8, we are using the base of 16. And it will increase from minus 1, then minus 2 power, then minus 3. That means before decimal, 0, 1, 2, the power is increasing in this order. And after decimal, minus 1, minus 2, minus 3, like this. Now let us see if there is the integer plus fraction part. Then combined conversions, how we're going to convert. Suppose number is 25.625 of 10. Okay. Then for integer part using repeated division method, and for fractional part using repeated multiplication method. Here we will note down the remainder. Here we will note down the integer part. Then combine both the results with the radix point. Move to next. The summary key conversion rules. This is consolidated all conversion pathways covered in the lesson. Quick reference. Decimal to binary, repeat division by 2, remainders, read bottom to top, decimal to octal, division by 8, 16, bottom to top, remainders use AF, 10 to 15, bind to decimal, positional expansion, power of 2, sum of bit into 2 to the power n, bind to octal, group of 3 bits from right, 4 bits from right, octal to hexadecimal, positional expansion, powers of 8, hex to decimal, positional expansion, powers of 16. Now a small question is there. Why do computers prefer binary but programmers use hexadecimal? Now, let us think. The computers are built from electronic circuits, transistors, that have only two stable states, 1 or 0. 1 means on and 0 means off. This makes binary ideal because it directly matches hardware. It's reliable and easy to implement electronically. All operations, logic, memory processing based on zeros and 1. So binary is a native language of computers. Now the second part, why programmers use hexadecimal. Why? Hexadecimal is preferred because it is compact. 1 hex digit equal to 4 binary bits. It is easier to read, write, and debug. Reduces errors when handling large binary values. Easier to handle actually. Now let us move to next. Summary or key takeaways, fractional. Repeated multiplication first is the core algorithm. Place values with negative powers to reverse. Integer and fractional parts are independent. Next. Now let's look at some standard CBSE style problems to practice our conversion skills. Convert 200 decimal number to binary, octal, hexadecimal. Verify each result by converting back to decimal, positional expansion. Now some CBSE style problems. Convert fractional decimal number to binary, to octal, and to decimal. You have to show the step-by-step multiplication or place value method for full marks. Some peer challenge questions, then quick quiz. Which is larger, if you have 16 or 111, 111, 102? We need to convert it into this binary number into hexadecimal number. Then we can decide, well, which is the larger. So from right side, we'll make group of 4 bits, then convert into its hexadecimal equivalent. Next, we can also write some Python program to convert one number system to another number system. Here I am taking one example, decimal to binary, octal, hexadecimal. After taking input from the user, suppose decimal number, conversion, use the functions, inbuilt functions, bin, the decimal number converted to binary, oct, decimal number convert to octal, and hex, decimal number convert to hexadecimal. Then display the results finally. What you are getting, if you enter decimal number 23, we will see binary equivalent 10111, octal equivalent 0O27, hexadecimal equivalent 0x17. Computer understands if you write in this manner, it is hexadecimal. If you write preceded with this, it is octal equivalent. So this is all for today's number system conversions, and thank you all.